In this video, we'll look at free fall. Free fall is basically an extension of the kinematics unit, dealing with vertical motion instead of horizontal motion. Free fall refers to any object that's in motion in which gravity is the only force acting on that object, pulling it downward towards the ground. Very similar to horizontal motion. However, there is one big constant. When you're doing kinematics, when you use the kinematic equations for horizontal motion, the acceleration could be anything. It can be positive, it can be negative, it can be tiny, 0.003, it can be huge, 3,000, doesn't really matter. The acceleration could be almost anything, but in horizontal motion, that's the way it works. In vertical motion, which is free fall, there's only one acceleration on Earth, and it's 9.81 meters per second squared. Specifically, it is negative 9.81 meters per second squared. It's always downward towards the Earth. So you're stuck. On Earth, there's only one acceleration. If you want more acceleration, go to another planet. That's the only way to really change it. All objects on Earth accelerate at negative 9.81 meters per second squared. This means, regardless of mass, all objects on Earth accelerate at the same rate, which gets us to a point that Galileo made a long, long time ago. Any two objects, regardless of mass, drop from the same height at the same time will hit the ground simultaneously. So literally, if I take a feather and a hammer, hold it up 1 meter in the air, let them go, if there is no air resistance, both the feather and the hammer would hit the ground at the exact same time. Our problem on Earth, obviously, is the air resistance, but there is a place you can go in this universe that has no air resistance, and that place would be to the moon. And that actual experiment was done on the moon. During the Apollo missions, astronauts were allowed to bring an object or two with them to the moon to experiment with. And one of the Apollo astronauts, David Scott, I think his name is, took a hammer and a feather and dropped it on the moon from the same height at the same time to see what happens. So let's see what happens.
Yeah, we thought they had both solar wind and then I found a drone in the
There he is. And there you go. Again, on the moon, there is no atmosphere. And since there is no atmosphere, there is no air resistance. And both the feather and the hammer are accelerated at the moon's gravity. You'll notice that as it fell at a much lower rate than what it would have done on Earth. But as they fell, they were accelerated at the same rate, and they ended up hitting the ground at the same time. So confirmation that that is indeed true. Experiments have since been done on Earth in large-scale vacuum chambers that, again, prove the same thing here. Because free fall and horizontal motion are so similar, the kinematic equations are applied to both. So we will use the same four kinematic equations that we learned about in free fall. That's why this is just an extension of the kinematics unit. One difference will be replacing the displacement with delta y. In horizontal motion, we use delta x because we're really moving on the x-axis of a coordinate plane. When we start dropping stuff or throwing things into the air, then we're dealing with the y-axis. So our displacement will be delta y. Another difference is we've got to pay a lot more attention to signs. in the kinematics, signs do come up. And if you watch the kinematics video, you notice there were some towards the end that I did with negative signs to imply that we can be changing directions and directions can be important. But the fact of the matter is, most people that are writing kinematic problems don't even consider direction when they write them. They just assume everything is moving to the right and they give you positive velocities for just about everything. In free fall, in vertical motion, that's not always the case. So we got to be careful about what's going on with the signs. First of all, acceleration will always be negative. It is always negative 9.81 meters per second squared because acceleration due to gravity is always down. I mean, it is the very thing that defines what down is towards the Earth. So the acceleration is always going to be a negative number. Velocity will be negative if the object is moving downward, if it's falling. Velocity will be positive if it's moving upward. Again, we have the same kind of thing in horizontal motion, positive to the right, negative to the left, and we saw that in kinematics. But it is really important here too, because of that negative acceleration, we're going to need some signs to play together very nicely. So we got to make sure that the falling object's getting negative velocity, and any object that is thrown upward into the air gets a positive velocity. Displacement delta y will be negative if the object is moving downward, if it's being dropped. It'll be positive if it's being thrown upward into the air. So again, your displacement, your delta y is positive going up, negative going down. And again, this is really important because we need these signs to play together nicely in the calculations. Be on the lookout for hidden numbers. There's nowhere that hidden numbers show up more frequently than in free fall. Acceleration is rarely mentioned in a question. It almost never says anything about gravity or acceleration. So you just have to figure out for yourself, okay, this thing is falling, gravity's at work, negative 9.81 meters per second squared is acceleration. When you're throwing something upward in the air, you know as it travels upward, it's going to slow down, slow down, slow down. So something has to be accelerating it. What accelerates it? Gravity, negative 9.81 meters per second squared. So rarely mentioned in a question, always used in vertical motion. So you got to remember to look for it and remember it. There's also often hidden velocities. There's usually a 0 meters per second somewhere. It'll be VI if you're dropping something. So if I'm dropping something out the window, the initial velocity, the velocity it starts at as I'm holding it in my hand is 0. If I'm throwing it upward, it's the final velocity that ends up being 0. If something goes up, it slows down, slows down, slows down, slows down, and for a split second, it stops. At the very top of its flight, it reaches a velocity of 0. So moving upward, VF is 0, and that is a very common hidden number. Same for kinematic equations, delta y instead of delta x. Again, because we're moving vertically now on the y-axis. And remember, all these a's, negative 9.81 meters per second squared. So as long as we're on Earth, you could even take that a out and just put the negative 9.81 meters per second squared because it's going to be there. You can put the negative 9.81 meters per second there. It's going to be there. As long as you're on Earth, a is negative 9.81 meters per second squared. On the moon, it would be different. On Mars, it would be different. On Jupiter, it would be different. As long as your question is framed around the Earth, you know what your a is automatically. Let's take a look at some math. The ball is dropped from a window 6 meters above the ground. How fast will the ball be traveling when it hits the ground? And you look at that and you see one number. 6 meters, that's delta y. All of these equations have 4 variables. To solve for something like how fast it'll be traveling when it hits the ground, VF, I have to have at least 2 more numbers, and that's where the hidden number thing comes in. First of all, dropping it. Whenever you're dropping something, VI is 0. And the assumption is this is on Earth. It doesn't say anything about it in the question. That's what we assume. And when we're on Earth, acceleration is negative 9.81 meters per second squared. So we really do have 3 numbers to work with in order to find our VF, even though the question only has 1 in it. Just like kinematics, you look at what you've got. delta y, vi, a, vf. Delta y, vi, a, vf. We use the last kinematic equation to solve that one. Again, the problem solving in this part is very important. Figuring out what equations you're going to use each time you're trying to solve a problem. Look at this list. Pick the equations that fit the list, or look for what's not in the list. What's not in the list here is t. Look for the equation that doesn't have t. Substitute and solve. Vi is 0. A is negative 9.81. Delta y is negative 6. I'm going to simplify. 0 squared is 0, so I'm just going to drop that totally out of the picture. 2 times negative 9.81 times negative 6 is 117.72 meters squared per second squared. Again, this is where signs become really important. My delta y is negative. Why is my delta y negative? Because I'm dropping it. Any delta is VF minus VI, or where you finish minus where you start. I finish at 0 on the ground, and I start at 6. 0 minus 6 is negative 6. I'm dropping something, so my delta y is negative. Acceleration is also negative because that's what it is on Earth. It always goes down towards the ground. These two negative numbers play together nicely to give me a positive number here for my squared velocity, so I can actually square root the thing. If I put a positive delta y in here, I will end up with a negative number here, and you can't square root a negative number unless you want to play with imaginary numbers. These two negatives take care of that for us and give us a positive number here. So the square root of 117.72 is 10.8. It is downward. And since this is a velocity, we do have to have the direction on it. And we can outright say downward, or we can put the negative sign back in front of this to indicate the downward direction and say negative 10.8 meters per second. So either 10.8 meters per second downward or negative 10.8 meters per second. That would be your final velocity. So like I said, more to deal with here with signs than what you deal with in kinematics. And that's the part that I think takes the most getting used to. Let's take a look at another example. This time we're going to throw a ball upward. Instead of dropping it, it's going to go up. It's thrown upward with a velocity of 15 meters per second, and that will be positive because it is upward. Up is positive velocity, down is negative. But that's all we have. There's no other numbers in this particular question. So we have to think about what else do I know? Well, I know VF is going to be 0. And the reason VF is 0 is because when you throw something in the air, it starts off moving quickly, and then it slows down, slows down, slows down, and then stops for a split second. That is your VF, where it stops for the split second. And we also know, since it's dealing with moving vertically, our acceleration is negative 9.81 meters per second squared. So again, there's only one number in the question, but we really have 3 numbers to work with. We want to know how high the ball is going to travel. That is delta y. So again, we picked the equation that has delta y, a, vf, and vi in it, and that is the same equation we used last time. But this time we have a number here and here to substitute in. Delta y is our variable. Vf is 0, so 0 meters per second squared. Vi is 15, so 15 meters per second squared. 2 is just 2. And the a is negative 9.81. And again, this is a positive velocity here because it's upward. 0 squared is 0. 0 meters squared per second squared. The unit gets squared too. 15 squared is 225. Again, the unit gets squared 2 meters squared per second squared. 2 times negative 9.81 is negative 19.62. I'll start by subtracting 225 from both sides. So that gives me negative 225 over here. Then I will divide both sides by the negative 19.62. And I get positive 11.5 meters. It is positive because I start at 0 and I end somewhere higher. My higher number minus 0 is going to be positive. So 11.5 meters upward. Again, to get that positive number on my answer, I got to make sure my signs are all correct going into the calculation. So again, signs are kind of important here. Let's take a look at some tricks and twists to this. Similar to what happened with kinematics and horizontal motion, a lot more hidden numbers. Drop from a window that is 12 meters up, that is our delta y. And since it will be dropped, we know its motion is going to be negative. It's going to be downward, so it's negative 12 meters. We're going down. We had a positive delta y over here because we were going up. Dropped is going down, so we have a negative delta y here. Only number in the question. So again, there's a couple of assumed values here. First of all, VI is 0 because we're dropping something. Whenever you're holding it in your hand out the window, it's not moving, so VI is 0. And the other thing we know, we're dropping it on Earth, so acceleration is negative 9.81 meters per second squared. We are looking for T. And the equation that has these four things in it is that one. Delta y equals VIT plus 1/2 AT squared. Now we run into the same issue that we ran into in kinematics. If I'm going to solve this one for T, my issue is I've got T in two different places. And one is squared and the other one is not, which makes it a pain to solve mathematically. Many, many years ago, when I first started teaching physics, I took this and I went to an algebra teacher and I said, how do I solve this? And she said, hold on, I have to remember how to do that. And she told me how to do it and I'm like, whew, no thank you. It is just far easier to take these three numbers that I have and use them to find VF, to add a fourth number to my list. I've got a delta y, I've got an a, and I've got a VI. I can just substitute those in and really quickly solve this out. 0 squared is 0, so we're just going to ignore that part and take it out of there, basically. And then 2 times negative 9.81 times negative 12 is really what we're going to do to simplify that side of the equation. VF squared is going to be equal to 235.44, and again, that's just 2 times negative 9.81 times negative 12. We've got to square root this, and when you do so, you get 15.3 meters per second. These negatives work together to give me a positive number here that I can actually square root. If I had this number positive and this number negative, I'd end up with a negative number there. When I tried to square root the negative number, it would tell me that that's impossible. That's an imaginary number. So these two negative signs work together to make this positive so that I can square root it and get the 15.3, but this is downward. We got to remember this object is falling, it is moving down. So technically speaking, it really is negative 15.3 meters per second. Now I can use this kinematic equation to find the time. Something a lot simpler. Again, this calculation here is going to take you less than a minute to do, because you're going to recognize that 0 squared is 0, and that's just 2 times negative 9.81 times negative 12. You're going to type that in the calculator, you're going to square root it, you're going to be done with it in less than a minute, no big deal. But this is 15.3 downwards, so when we go to substitute this in here, we are going to want to make that number negative, because mathematically we can't put downward into the equation. So we do want to make sure we bring it over there, that is a negative number, because we need these negative signs to play nicely too. VI is 0, A is negative 9.81. I can get rid of that. Gives me this. Divide both sides by negative 9.81. Negative 15.3 divided by negative 9.81 is 1.56. Meters per second divided by meters per second squared. The meters cancel out. One of the seconds cancel out. Seconds is in the denominator. The denominator, so it moves up. That's where the seconds comes from. So again, very similar to the same kind of issue we had with this equation in just horizontal motion. Don't ever, ever, ever use that equation to solve for t. Find the VF first and then use this equation to solve for time. It'll save you a lot of time and it will help prevent mistakes. All right, let's try this one. This is different. A ball is thrown downward from a height of 20 meters with a velocity of 10 meters per second. How long will it take to hit the ground? The initial velocity is 10 meters per second. It is downward, so it is negative. It's falling 20 meters, so delta y is negative 20 meters. Again, downward is always negative. Throwing it down, negative 10 meters per second. Going down 20 meters is negative. The third number is a hidden number. That's the acceleration, negative 9.81. How long will it take? T. Again, we aren't going to mess with delta x or delta y equals vi t plus 1/2 at squared. Not worth the time or the headache. Not when we have this equation that we can use instead. VF squared equals vi squared plus 2a delta y. We're going to use it to find VF, and then we can use one of the other equations to solve for t. Substitute. Vi is negative 10. We'll be squaring that. A is 9.81. Delta y is negative 20. Simplify. Negative 10 squared is 100 meters squared per second squared because the unit also gets squared. 2 times negative 9.81 times negative 20 is positive 392.4. Meters times meters gives us meters squared on top. Second squared is still on the bottom. Add those together. We get positive 492.4. Square root it. And we get 22.2 meters per second downward. Downward because that's the direction we're moving. The negative sign doesn't come through in the answer because we had to have these negatives cancel out to give us a positive down here so that we could actually square root it. So we end up with a positive number for our answer, 22.2, but that is downward. So when we go to substitute it into this equation to find t, we want to make sure we put that in as a negative number. You can't put downward into the equation, so we have to make sure we put it in as negative, 22.2. Vi is negative 10, A is negative 9.81. Solve this for t. It's negative 10 meters per second squared. So I'm going to add 10 meters per second squared to both sides. That gives me negative 12.2 over here. Then I'll divide by negative 9.81 to give me a nice positive time. Your time should never end up negative. Time doesn't move backwards. So that negative sign over here is important. This negative sign over here is important because when they play together in that division, they give us a positive answer. And there you have it. Again, similar to kinematics, a lot more hidden numbers. Delta y's instead of delta x's. And we have this acceleration all the time of negative 9.81 meters per second squared. Like I said, you got to pay a lot more attention to signs in this than you do with horizontal motion because they're really important. We don't want to end up having to square root negative numbers. We need our signs to work out when we calculate times to give us positive times, things of that nature.